Let's talk about some of the basic algebraic properties of matrix arithmetic. So I've got one column here for addition and one column here for multiplication, just so that we can compare and contrast. So the first big difference we saw is the commutative property. So addition is still commutative for matrices, but we saw that matrix multiplication is not commutative. So A times B is not necessarily the same as B times A. The associative property does still hold for both instances. If we add two matrices and then add a third one to it, it's the same thing as if we first added the first two and then added the third one to it. So the difference here is the order in which the operations is carried out, as indicated by the parentheses, not the order in which they're written on the page. That's this one. And so multiplication is also associative. If you have three things written in the same order, then it doesn't matter if you multiply the second two together first or the first two together first, you'll still get the same thing either way. We also have the identity property. So there is a matrix B such that when you add it to anything else, nothing happens. This is the additive identity, which we call 0, and it's the zero matrix. It's the matrix of all zeros. There's also a multiplicative identity. So there's a matrix B such that when you multiply it against anything else on either side, nothing happens. And we call it the identity matrix, and it's this one that looks like ones down the diagonal and then zeros everywhere else in the matrix. There's also the idea of inverses, and here's another difference. So for any matrix A, there's an additive inverse B, such that if you add A to B, you get the additive identity. And we call B the negative of A, and it's just minus 1 times A. Things are different, however, if we look at the multiplicative version. So for a given A, there may or may not be a B that you can multiply it by, such that AB times BA is equal to I. Now, if there is such a matrix, then we say that A is invertible, and we call B the inverse of A, and we write it like this, A to the minus 1. But it doesn't necessarily always exist. Now this is weird. It's a departure from numbers, because with numbers, the only thing that does not have a multiplicative inverse is 0. For anything other than 0, you can take the reciprocal. So for any x that's not equal to 0, you can take 1 over x. And if you multiply that against x, you'll get back to 1. But for matrices, there are lots of things besides 0 which are not invertible, and that's a big difference. The distributive property still holds for matrices, just like it does for numbers. But the zero divisor property does not. So for numbers, you know that if a product of two things is equal to 0, then one of those two numbers has to equal to 0. But for matrices, you can have AB equals 0 without having either A or B equal to 0. So let's see an example of that. So for an example of zero divisors, let's take A to be 2, 2, minus 1, minus 1, and B to be the matrix 1, minus 1, 2, minus 2. Okay, then if we do A times B, what do we have? So we've got 2, 2, minus 1, minus 1, 1, minus 1, 2, minus 2. And multiplying these together, let's see. Well, we're going to have this one dotted with this one. So we have 2 minus 2. And then we're going to have this one dotted with this one. So we have minus 2 plus 2. And then we have this one dotted with this one. So that gives us, again, 2 minus 2. And then we have this one dotted with this one, and that's minus 2 plus 2. So you can see that we're going to get a 0 in each place, the zero matrix. But A and B are clearly not equal to 0. Okay, so this has some maybe unexpected side effects. So for instance, we're also used to thinking that if you have say AC equals AD, you want to think that you can cancel, and from that get, and from that get that C is equal to D. So, is this still true? Well, the reason for this cancellation law, or the reason why we believe it to be true, is that if we have AC equals AD, then we can make this into AC minus AD equal 0 by subtracting from both sides. And then if we factor out the A, we have AC minus D equals 0. And so then we want to conclude that either A or C minus D is equal to 0. And if we expect that it's C minus D, then that would tell us that C is equal to D. But that falls down. So let's look at, we'll keep the same A that we had above, and let's take C to be 1 minus 2 minus 2, 0, and D to be 0, 3 minus 4, 10. And then if we work out AC, this is going to be, so we've got 2 minus 1, 2 minus 1. This is the A that from the previous example. And what do I get here? So I'm going to get 4 minus 4, 4 minus 4. And if we look at A times D, then we have 2, 2 minus 1 times 0, 3 minus 4, 10. And so now we're going to have 4 minus 4, 4 minus 4 again. So AC is equal to AD, but as you can see, C is definitely not equal to D. So that cancellation property no longer holds.